Dr. Valentino Cooper. Thank you for joining us on QED with Dr. B.
It's my pleasure to be here. Thank you for having me.
You got it. So this show is about energy. So what specific aspects do you look at in energy?
We're very much interested in what I like to call the electron economy, right? So how do we move electrons? How do we create electrons and store those electrons? So you can think of things like solar cells. Those are important materials that capture sunlight that we then use as electricity. We also have materials that we can use to convert that electricity into something that we can store it and use it at another time. So we can take that electricity and either store it in a lithium-ion battery, or we can convert it to something like a fuel, like hydrogen, that can then be used in a fuel cell in cars.
So it's safe to say you study materials at the atomic level to inform us about solutions at a larger scale. Talk about how your research at the atomic level can actually impact on a large scale in terms of energy solutions.
So, as you know, everything around us is made of atoms, right? And what we really are trying to do is understand how to rearrange these atoms in a way that we can either store electricity or use them to convert something from one form to another. If I take certain elements and I put them together, what happens to that material? Can that material be a more efficient solar cell? Can that material store more electricity? Can that material convert mechanical stress into electricity? And so a lot of what I do actually comes down to materials that do that kind of conversions, which are referred to as piezoelectrics. So these are materials that can convert mechanical stress into electricity or vice versa. You can use electricity to change the shape of the material. A very good application is naval sonar. You send out a sound wave, it bounces off a structure, say a dolphin, and it comes back and it hits the piezoelectric, and it can then convert that sound wave into something that you can see on screen. Another very prominent application of piezoelectrics are ultrasound images. These are the type of materials that you use to actually see a baby in utero before it's born. The other way we can use piezoelectrics for energy applications is to use the reverse effect. So we apply a little bit of electric field and we can change the shape of that material. And in fact, this is what is used in diesel engines to control the fuel to gas ratio. So you can have very precise control over how much fuel or how much diesel you're delivering.
Tell us about your latest research.
My latest research, now we are looking at the cathode materials in batteries. A lithium-ion battery has a cathode and an anode, so a positive side and a negative side. And what we're trying to understand is what happens to that positive side as we charge and recharge our batteries. What can happen is when you take the lithium out of your cathode, it can transform into something that you just cannot put the lithium back into. And if you can't put the lithium back into it, then you can't recharge it, right? And so that's when we start to have to throw away the battery.
Got it. So your work is looking at how to make batteries retain more energy for a longer period of time and make batteries more efficient at being rechargeable.
Yes. How can it prolong the life of my battery?
How do you use computers in your research, and just how cool is it to actually have the fastest computer at your fingertips?
Frontier is really a level up of all the computers that we've seen before. Now we can actually model systems that are much, much larger. So the method that I use actually is based on understanding what the electrons in a material are doing. When I started out research, we were looking at systems that only had somewhere around 100 atoms. But now with a machine as large as Frontier, we can look at things that are 1 million atoms. So one of the things we really want to understand is what is the most stable structure of a material. And so what we do in our simulations is we start off with a guess. We have a system and we put atoms in a certain place. But because of the way the atoms and the electrons interact, that may not be the most stable structure. And so what we try to do is understand, if I start off with this particular configuration of atoms, what is the actual preferred structure? Where do those atoms want to be? And then once we know what that structure is, we know what the electrons are doing. So we can tell you, is this a material that, for example, can be used as a catalyst where you can use it to convert one form of energy to another, or to have a high capacity battery? Is it a material that we can use as an efficient solar cell?
Sure. That's interesting. So it's almost like you had a 10,000 piece puzzle, and you had the 10,000 piece puzzle pieces all around there, and we can take our time as humans to try to systematically put 1, 2, and 3 and build that. Or you can put those 10,000 pieces in a supercomputer and they can simulate all the possible outcomes.
That is exactly right.
What's next on the horizon for your research?
For our research, the next thing that we're looking at is actually the material that goes between the batteries. In most lithium-ion batteries now, between them you have a liquid. Unfortunately, that liquid is not a very good barrier. And so what can happen is that your lithium can start to form little bridges between your positive side and your negative side. When that happens, it causes a short. So that means instead of your electrons going through your circuit to, say, your light bulb to turn it on, it goes through your battery. And so then you never see your light bulb turn on. The other danger in that is it's a flammable liquid. And so what we're looking at is what type of solid materials could we put in between there that would prevent that dendrite formation and would be a lot more stable or less flammable than those liquids. And so we're now looking at polymers that can go between those materials.
How is it to work at the Oak Ridge National Laboratory?
For a person like me that models materials on a computer, I get to meet everyday scientists that are actually making these materials. So I get to see how the things I predict can actually be made in the real life and how they work. And I get a little bit of feedback, right? They tell me whether I'm wrong or whether I'm right, and I just love that experience.
Dr. Cooper, thank you so much for being on QED with Dr. B.
Thank you for having me. I had a great time.
Absolute pleasure.